All right, so primary colors are those hues that when combined create white light. It's like a formal definition. It's our review session of what we're going to talk about. Oh, yay, look, you're actually charging.
Yay.
Oh. I promise you part 2 is more exciting than part 1 of this color lecture. Secondary colors are the result of mixing 2 primary colors.
What's the primary one?
Sorry, what?
What's the primary?
Primary colors are red, green, and blue.
Okay.
So these are the primary colors, red, green, blue. And then these are the secondary colors, magenta, cyan, yellow, or amber. Complementary colors, a primary and a secondary hue that when combined create white in light and are opposite on the color triangle. So next class to review, I'm going to set this up for all of them. And we're going to look at the mixing of a primary and a secondary, so the complementarily, right? So we'll look at blue with amber mixing to white. We'll look at red with cyan mixing to white. And we'll look at green to magenta mixing to white. Yeah?
So it wouldn't be complementary if you mixed amber with red.
Correct, because in order to get amber, you have to use red and green, right? Or essentially, those are the wavelengths that are coming through the gel. Even if it isn't a amber gel, those are the wavelengths that gel is allowing through the filter, right? So it can't be complementary because you need in the amber you need the blue to get to the white because you need all the elements of the spectrum to get white light. Yeah.
What happens if you mix 2 secondary colors?
You get a totally different color, and that's what's, so I'm going to go way back here. So that's what we were doing in grad school with chromaticity. Is so you would pick like 2, maybe they would be 2 secondary colors, and you would plot 2 points on this mamma jamma, and then anything in between is a color you could theoretically get between those 2 points. So there's like a mathy way, a mathy geometry, physicsy kind of way to get there. And so like, but chromaticity and chromaticity charts is like, it's fun, but it is. Great. So here's another visual representation of the same thing. Colors from different light fixtures are superimposed here. So again, we've got the 3 primaries here, and we have secondaries. This one's calling this one violet. This one's British. Just don't be afraid. So we still have sort of some things going on. But here we have blue and we have amber mixing to white, right? Blue and amber mixing to white. Here we have red and cyan mixing to white. So it's a secondary and its opposite primary being complementary. So again, here's the visible spectrum. This has to do with the actual wavelength, and that's sort of like the size, like, the size of the sine wave. If it's like real big, I can't remember if it's real big. If it's real big, I think it's red.
Yeah.
And if it's real small, then it's violet. Right? But that's super science. Oh my God, with all the science. Here's another version of the chromaticity chart, right? So if you're looking at this sine wave, because that's what this is, mathy sine wave from all your nightmares or dreams. So here you've got the blue, you've got the green, and you've got the red. And technically anything on this line is part of the wavelength, but it's sitting in the infrared or the ultraviolet spectrum, or like close to it. So it's sort of not actually on the sine wave. Don't worry about that. That's probably really confusing, but it's like, yeah.
Why is the green so much bigger than the other?
Because green is the most visible part of the spectrum, weirdly.
I thought it was green and yellow.
It is green and yellow.
Yellow's tiny.
Yeah, but green, well, from everything I've learned, green is the more visible part of the spectrum. But yeah, yellow is too. But it is tiny because less things, in order to get amber, technically, you need to mix these two together, right? I don't know the full answer to that. This here, it has to do with the color temperature of what light is emitting. Like, so, for instance, the color temperature of these little tiny, what time is it? Okay. All right, we're getting real close. The color temperature of these little guys, even at their brightest, is still pretty warm, right? So it would actually be sitting more on this side of this line. Whereas a source 4 at its brightest would be sitting a little bit closer to the blue part of the spectrum because they're actually a fairly white, balanced light, right? So it depends on what kind of lighting instrument you're using to begin with before you start filtering out the light. That impacts the colors that you have, right? Did you know that, or is that something it's just making sense in your? Yeah. So like your Fresnels tend to be a little bit warmer to begin with. So if you want to combat amber drift, because that might be something you want to do, you might want to combat amber drift so that at a low level, that means you have to pick a more medium, more saturated blue, so that when it gets to a lower level, and I'll show this next class, so when it gets to a lower level, you can combat that amber drift. What was your question?
Is that why like HIDs, you know, the ones that use like tungsten or something, always
Yeah.
come out like super like punchy white?
Yeah. So they sit even more closer to this side of that, you know, so yeah. So you would have to figure out where in the Kelvin spectrum, right, which is the same, spectrum that scientists use to measure the light out of suns as well, right? So how warm or cool they are. What?
I said it's a lot.
It's
Yeah.
a lot. This is why this is a 2-day color lecture and not a 1-day. Okay, I'm gonna stop there. We'll pick this back up. I will have my shit figured out. You can go ahead and you already stop it. Or you guys stop it.